Okay, so the plan for today, still kind of finishing up the intro to the course, finishing the discussion from day one from our last class meeting, doing one problem to review section 6.1, and then talking about 6.2. Just a reminder, this is a hybrid Zoom class, so if we don't quite get through everything in today's plan, then we might kick a problem or two to a supplement that I'll post later on this week. Or if we do get through everything, then we'll kind of take the hybrid component to be the outside of class work that you're doing, reviewing the syllabus, all of the stuff on Blackboard, getting signed on uh, to the WebAssign system, all of that kind of stuff. So that's all I'm taking to be kind of part of the hybrid material for this week. And there might be another supplemental lecture posted depending on how far we get today. There are some new homework sections up that I just posted just before class. So the rest of chapter 5 and a few sections in the chapter 6 are available now. So you can work ahead if you want to. Okay, and then one other thing that I do most days is I'll have a quote of the day. So the quote of the day for today is from P.T. Barnum, the famous circus, entrepreneur. And, it's a bit of a long quote, but the main crux of it is true economy consists in making the income exceed the outgo, uh, and that we want to maintain a margin in favor of the income. So he's talking more financially in this case, but I think this general idea of margin applies very broadly in life, and it's something that I have seen make a big impact in my life. One very concrete example of that is driving through traffic. I tend to get frustrated at people. I think that's pretty common, right? But I noticed that if I'm in a rush to get somewhere, if I have left myself no margin, if I have just enough time on Google Maps to get to a place on time, I tend to be a lot more frustrated with folks than if I leave 5 minutes early, give myself that little bit of buffer. And then if, somebody stops at the yellow light instead of going through, then it's like, okay, that's not a big deal. Um, so I think margin in life in general is very important. Um, and when you have margin, often catastrophes become inconveniences. And when you don't have margin, often the reverse is true. So how does that apply to this course or to schooling? Well, if you're looking at the due dates for the homework for this first week or for really any week, and you see the due dates are they're all going to be posted as due on Sunday, except for the very last week of class. But you see the due date is Sunday at 11:59 p.m. If you say, okay, I could probably knock that homework out in 3 hours, I'll start it Sunday at 9 p.m. Well, then if anything goes wrong, if anything happens, power failure, tech issue, maybe you didn't understand that material as well as you thought, or it was more challenging than you expected, something in your personal life happens, since you have no margin, you're not going to get that homework completed on time. If you built in margin, if you say, okay, instead of doing it in one big 3 hour chunk, as an aside, that's not a great way to learn the material either, doing it under stress all at once. If you say instead of doing that, I'm going to take 30 minutes a day every day of the week, Monday through Sunday. Uh, if something goes wrong on Tuesday when you have your 30 minutes allocated to work through a couple of the homework problems, well, not a big deal. You just push that time to Wednesday, right? There's a lot of margin, there's a lot of buffer. That, thing that could be a catastrophe just becomes an inconvenience, a little technical issue. Okay, we'll get it worked out by tomorrow, and I still have plenty of time to get the homework in. This is an even bigger deal with exams. Especially in this course, there are no exam due date extensions because there's such a big exam window, roughly a week for each of the exams. Um, so, waiting until the day the exam is due or even the day before leaves you very little margin if something goes wrong. If you plan to take an exam that's due on Sunday, you plan to take it on Wednesday. If something goes wrong, you have quite a bit of time to work that out or to get in touch with me, get in touch with the WebAssign folks, whatever it may be. If you wait until Saturday night or even worse, Sunday night to start that exam, that's really playing with fire. So I would strongly recommend, I think this is probably the uh, number one component to success in college is building in margin. Not procrastinating and planning to get things done ahead of time. it's also the number one, I think, most difficult thing to do. And, I'm not in any way saying that I never procrastinate or I always build in the right amount of margin. So, um, it doesn't always go to plan, but the more often you do build in margin, I think the less stressful things are and the better and more smoothly things work out. So that's the quote of the day today about margin. Um, there's another quote on margin that I might even, it might be the quote of the day later in the course, but it's goes something like, build margin into your life so you have time for the things that are important, not merely for those things that are urgent. So, right, with little margin, you tend to prioritize the urgent things, and the maybe deeply important things uh, get pushed back and pushed back further. Okay, so just a few thoughts about college in general. I think this might be a little less applicable to Calc 2, but this is kind of wrapping up our first day discussion. And this is something a little different that I've thrown into the intro material starting this semester. So, um, you know, uh, making it to Calc 2 means you probably have a pretty good educational background behind you, but I think I'm going to throw this in anyway, just because I think this material is valuable. It's something that I didn't appreciate as a student or frankly as a faculty member, a lot of this until somewhat recently. Um, so the first is the difference between the goals of different coursework. There is program-specific coursework, kind of program-related coursework. I'm kind of splitting these out, not everybody does. And then there's general education or core coursework. So one example might be if you're going for a business degree, your actual business courses might be your program-specific coursework. Programming related might be something like accounting. It's like you're not going to be an accountant, but you need to know a little bit about reading financial statements in order to work in business. And general education coursework might be like your humanities or art course. Um, or nursing might be your nursing courses are your program specific. Something like maybe statistics is program related. You're going to use statistics as part of being a nurse, but um, you're not going to be a statistician. And gen ed might be your philosophy course. So there's more and more a movement these days among, to be fair, both students and kind of among faculty members as well, basically saying, well, if it's not my program specific coursework, why should I take it? Why should it be required? Right? If I'm going to be a nurse, why should I have to take an art course? Or if I'm going to go into business, why should I have to take a philosophy course? Or, for those of us going into STEM, if I'm going into STEM, why do I have to take this silly English literature course? Um, why can't I, or this is implicit in the question, when am I going to use this material or this course work in my job? So what's the answer to that question? And I want to use as a primer to that answer this quote from Christoph from The Truman Show. This is a movie a Jim Carrey movie. He played a guy, Truman, and in the crux of the show, it's a little bit of an older show now, so you might not have seen it or even heard about it, but the crux is that his entire life is like a true reality show. He's living in this constructed environment with cameras everywhere. All of the people he interacts with are actors, but he doesn't know it. He was born in this environment and raised, and his whole life is an actual kind of reality show. And at one point somebody asked the like director mastermind guy Christoph something along the lines of like how does he not realize like occasionally glitches will happen or something will go wrong or uh how does he not realize this after 30 years or something? How does he not realize he's in a show? And Christoph says we accept the reality of the world with which we're presented. It's as simple as that. And I think that's really the argument for general education is each one of us is presented with a certain worldview based on where we live, our life experiences, whatever it may be, our geographic location, the things that our family thinks and believes and does. And these general education, these core courses, your philosophy, your basic math for folks not going into STEM, your um, humanities courses, your literature courses, uh, they provide glimpses into different worlds. they present different worlds to you so that you have a rounded view of the fact that, at least the fact that other people have different experiences than you, and what their experiences might look like, what their expertises might look like, and what the values that those different experiences and worldviews could bring to your career and to your life. And I think that's really the point of a degree, an associate's degree or a bachelor's degree, master's degree, really is this kind of general education component. There are credentials, and I, don't at all mean to disparage those. There are things like programming boot camps and things like that that really only have program specific coursework, or there are trade schools where it's just program specific coursework. And there's certainly a place for that. That's absolutely valuable. But I think that's the difference between those types of credentials and a degree, is really this general education core. So I know that in Calc 2, we're, depending on what major you're looking at, you're either in the very closely program related coursework doing Calc 2, or in program specific coursework, perhaps. If you're going into mathematics or applied math, you might call this program specific. Or if you're going into something like engineering, you might call it program related. But this is, if most people in STEM say, where will I use Calc 2 in my career? I can give them very tangible examples. But you know, don't look down on your English literature course because they can't tell you when you're gonna, use Jane Austen in your engineering career. There's real value that's brought uh, to your education from those courses as well. I think also the goal of college, maybe the primary underlying foundational goal, is to become a lifelong learner, especially these days. Um, Information and knowledge and understanding changes so quickly that, when you graduate from college and get into your career, you're going to have to continually learn new things, adapt to new areas, and you might decide 10 years into a career that you want to pivot and do something completely different. And becoming a lifelong learner really enables all of that. Not to mention that it's just, I think, very rewarding and fulfilling. I think there's something very human about wanting to continue learning and mastering new things. So learning to think critically, and learning how to learn for your particular, psychology, your particular learning styles. Um, And also, I should mention that every one of us will be a teacher at some point in our lives. So continuing to be a learner enables you to be a better teacher, whether that's in your career training somebody who is hired at the same level as you, or you move up to supervisor and have to onboard folks and train them in how you want the department to work, um, or whether it's you have kids and you're trying to teach your kids random things about the world, or whether you're trying to help them with their math homework or their reading homework or whatever it may be. So we're all also teachers at many points in our lives too. Um, Something that I realized maybe a little bit too late in my college career, I did realize this a little earlier than some of the other stuff though, is that success in college is as much about mastery of time management and understanding expectations as it is about mastery of the coursework or the course material. Don't get me wrong, mastery of the course material is crucial, very important. Um, but again, kind of, looking back at this margin quote, um, you know, developing good time management skills, which is even more crucial in a remote or online environment, um, I think is one of the biggest determinants of success. And like I said, nobody does it perfectly. I don't do it perfectly. Your instructors don't do it perfectly. Our administrators don't do it perfectly. Everybody, uh, is sometimes better and sometimes worse at this, but um, trying to over time, you know, make the times that you're on point, make those better and make those more frequent. And also understanding expectations, right? Understanding things like, um, there's a level of professionalism that's expected in the classroom. Being on time to class is expected. If you're 5 minutes late one time, that's not the end of the world. If you're 5 or 10 minutes late to every class, that's not really meeting expectations. You might be missing out on important announcements or something like that. It's especially tempting with the Zoom or online class where well, I should say Zoom, where we have a meeting, but the lectures are recorded and you can watch it later. It's very easy to just say, oh, I'm just going to watch the lecture later, maybe never quite get around to it, or maybe watch the lecture at midnight when you're half falling asleep. Um, so understand the expectations of the courses. And of course, that goes for the course policies as well. What are the policies for exams? What's the grading structure? I learned the hard way that, faculty stick to those expectations quite closely, really out of fairness to all the students. Um, so I did poorly in one of my first semester freshman courses, even though I had gotten great scores on all of the exams. And I got a bad grade at the end, and I went to the instructor and said, like, hey, why did I get a bad grade? I did great on all the exams. He was like, you're majoring in math. You can see how the grades are calculated. What did you think you were going to get if you didn't do half the homework? It's like, yeah, but I did all the exams. I clearly understand it. It's like, these are the expectations, right? So understanding expectations and meeting them is also crucial. Um, there's also this analogy that I kind of like. Some courses are more like a train and some are more like a zoo. So some are like, if you're on a train from Pittsburgh to New York and you fall off in Scranton, like from Scranton to New York, that ride is useless to you. You're stuck in Scranton. And some courses are a little more like a zoo where you're going around the zoo and you see the elephant and you enjoy it, and you see the giraffe and you enjoy it, and you were texting somebody on your phone and walked past the zebra, but you see the monkey on the other side and you enjoy that. You lost the zebra, or whichever one you lost. I think it was the zebra. You lost the zebra. And that would have been cool to see it, but you know, that missing that part, the whole is only detrimented by that part. uh, where, right, if you fall off the train, it's like the rest of the train ride is useless to you. And math tends to be more like the train analogy, where a lot of your courses, like maybe literature or humanities, tend to be a little bit more like the zoo analogy. So keeping up with the material, and again, especially in math, making sure that keeping up with the material, with that time management and so on, uh, even more crucial than usual. Um, and there's something to be said about, in a given course, there is the material to be covered. There's, just kind of the rote memory of how does this thing work. But there's also the method. There's also the way of thinking, what is the philosophical approach to the material? Um, Something to kind of keep in the back of your mind. And I guess I'll end this with one last question. And this is a question, well, I guess it's two questions, but I would recommend actually taking 10-15 minutes, writing down an answer, or say one paragraph or so answer to each of these in your notebook. It's not, don't hand it in to me, or it's not for a grade or anything, but, you know, you're spending a lot of time and effort and money to learn things, to end up knowing things, right, by taking these courses. So ask yourself, to you, from your point of view, what does it mean to know something? And what does it mean to learn something? These are not easy questions. These aren't questions that you can just look up the answer to. And these are questions that philosophers in the field of epistemology um, debate back and forth, to this day, and argue about, and what does it mean to know something? But think about what that means to you. I think that's good to think about, especially in the more technical fields. When I say that I know that 2x is the derivative of x squared, that kind of means something different than when I say that, like, you know, I know that, I don't know that, if I pick up a book and let go of it, it's going to fall down. They, the, those two statements kind of mean something a little bit different, even though we use the same word in both cases. And there are a lot of other statements as well, right? Like, I know what my name is, or that means something different still. All right, so that was the last bit of thoughts from that discussion in the first class. I think that is all that I had to mention there. All right, so let's move on to the material then. So section 6.1, this should be review, but we might need to dust off the cobwebs a little bit. So we're going to do one example in 6.1, computing areas between curves. Something to recall is that the integral a to b f of x dx represents the signed area between the curve y equals f of x and the x-axis, and between the vertical lines x equals a and x equals b. So this is signed area in the sense that if f is positive, this is going to be a positive area. Oops. And if f is negative, the area will be taken to be negative. So if we want the absolute area, we might have to make sure that our top and bottom curve, so to speak, are kind of in order. We can say that if f is bigger than or equal to g on the interval ab, then the integral of f minus g from a to b represents the absolute area between the curves y equals f of x and y equals g of x between x equals a and x equals b. Note that this is a generalization of the previous statement. If we take f to be non-negative and g to be 0, then we get the previous statement. Or well, I suppose we get a particular case of the previous statement. And note that the integral of the difference is the difference of the integrals by linearity of integration. It's the difference between the signed areas related to f and to g. Okay, so let's take a look at this example. Let's find the area of the region bounded by these curves, 4x plus y squared equals 12 and x equals y. So we have two curves here. Let's figure out what's going on with the first curve. If I solve this for x in terms of the other stuff, I see that x is what? Minus 1/4 y squared plus 12 over 4 plus 3. If my x and y were switched, if I had y equals negative 1/4 x squared plus 3, that would be a parabola opening down. Right? It would look something like this if my x and y were switched. But switching x and y flips me over the line y equals x. So this is going to be a parabola opening to the left. Right? In other words, when y is 0, x is 3. When y is a little bit positive or a little bit negative, y squared is a little bit positive, and x will be 0. Let me make that a little more symmetric looking. I think that looks a little better. So we have a parabola opening to the left. So the black curve represents the graph of that equation. Jeez. Office recently updated something, and now everything looks a little bit different. And anytime I do anything in Office, it has some pop-up that has to tell me something immediately. So I've been spending the whole week closing random pop-ups. I don't know if you could see that, but when I clicked on the pen, it popped up with some new piece of information that it needed to tell me urgently. Okay. And then in blue, we'll draw x equals y, of course, just the 45-degree line. And we see that there is one area that is enclosed here, and that's this area. And I want to find this area. Now I can integrate from x equals a to x equals b, or maybe 3. And I know that when I integrate this, I'm going to be integrating top function minus bottom function. So over here, I'm going to be imagining kind of my Riemann sums. My little Riemann boxes are going to look like that. Blue will be my top function, black my bottom function. This doesn't look too bad. But I have this little issue, right? So for these three boxes, for this area off to the left, this bit of the area off to the left, My top function is the blue function, my bottom function is the black function. But over here, kind of to the right, my top function is one leg of the black function, my bottom function is the other leg of the black function. I have two regimes that I have to deal with. So if I'm integrating dx, number one, I have two regimes I need to deal with. The left bit, where blue is the top and black is the bottom, and the right bit, where the different legs of the black function are the top and the bottom. That's kind of annoying. I mean, it's not insurmountable, but it's annoying. The other challenge I need to deal with is this black function isn't really properly a function. So I need to look at the top leg and the bottom leg separately, and that also seems like it's going to be a bit of a pain, right? I have y equals plus or minus square root of 12 minus 4x. So I have this plus and minus and square root and all that. So I could probably go this route, but it's going to be a hassle. It might be a little nicer to kind of change my perspective. If I integrate over y, I need a little more y-axis down here. There we go. If I integrate from y equals a to y equals b, and I think of my Riemann box as looking like this, I notice from this perspective, my black function really is a function, and so is my blue. My black function is always the top function. It's always associated with the higher x value. And the blue function is always the bottom function. It's always associated with the lower x value. This is going to be a much nicer integral to do. I probably want to integrate this dy. So in any of these kind of very geometric problems, it's always worth just keeping in mind that there are often different perspectives you can take. And that's super helpful here. Now, if I'm integrating dy, I want x equals f of y for my top function and x equals g of y for my bottom function. So what's my area going to be? I guess I'll do it in green. I'm going to leave my bounds off for the time being. We need to go and find what those are. But I want to integrate top minus bottom. Right? This statement about functions where the independent variable is x, we can just switch the independent variable to y and the dependent variable to x, and the same statement is going to apply. So I want to integrate top minus bottom, or I want to integrate the black f of y minus the blue g of y, which is just y, dy. So I've got my integrand figured out. I do need to find my bounds of integration. I need to find out what are a and b. So I need to find the intersection between these two curves. So when does f of y equals g of y? Well, that's when negative 1/4 y squared plus 3 equals y. Or what would that be? 1/4 y squared plus y minus 3 equals 0. Let's multiply by 4 to clear that fraction out. And I think we can see this is going to be y plus 6 times y minus 2 equals 0. And y is going to be either negative 6 or positive 2. There's negative 6 and positive 2. So I'm integrating over the y-axis from negative 6 to positive 2. Of the black curve, x equals f of y, the top curve from the perspective of, tilted 45 degrees kind of, minus the bottom curve minus the blue curve, g of y equals y. And this should be a pretty trivial integral to do. So this is going to be, we just integrate term by term. We get y cubed over 3, hits the negative 1/4. 3 integrates to 3y, minus 1/2 y squared, evaluated from -6 to +2. And from this point on, it's just arithmetic. I will let you take it from there. But I think a couple of good points to make here. I'm just reminding ourselves how the signed areas and so on of regions work. Reminding ourselves that sometimes a change in perspective is super helpful when we're in the geometric world. And just how we can use that to our advantage to make the problem simpler and to make the integral simpler as well, right? Integrating a polynomial is easier than integrating a square root. And having to do one integral is better than having to do two different integrals. Any questions on this one?
Yeah, I have one quick question.
Sure.
So when you started out the problem, did you set x as the function of y with the pre-thought that you were going to have the parameters in terms of y?
Um, yeah, so kind of as an instructor, I always cheat a little bit because obviously I work through the problems in advance. But what I would say is if you came to me with this problem and I had never seen it before, I mean, it's always a little bit of guesswork on my part because I've done the problem a couple of times, right? But I
Hmm.
think I would do this anyway, even if I wasn't sure that I was going to change perspectives, so to speak. And the
Okay.
reason is that I'm much more used to looking at output variable by itself as a function of other variable squared. I know what this pattern looks like, um, but looking at output variable, if I did like y squared equals 12 minus 4x, I mean, I'm not really sure what that looks like, or at least I have to think a little harder to figure out what that looks like. But I know
Okay.
that this looks like a quadratic, but just with x and y flipped from the normal like up and down quadratics that we're, you know, mostly used to looking at from, algebra courses. So I probably would have taken this approach anyway so that I could say, okay, I recognize that this is a quadratic opening towards the negative side of the dependent variable, but here the dependent variable is x. So I know it's opening towards the negative side of x, in other words, to the left.
Okay. Thank you.
Sure. Yeah. Yeah, a lot of math is pattern recognition. And if you don't recognize the pattern right away, you ask, can I like force this into the mold of a pattern that I do recognize, even if I need to pull, a little mental gymnastics here or there, like, changing the independent and dependent variables. That's easier for me to keep track of, okay, X is the dependent variable, Y independent here. That's easier for me to keep track of than to establish a new mental pattern. Um, at least I think so, like looking at something like this, it just pops a little less to my eye than something like this that I'm more used to looking at. Uh, but that being said, if if you really like looking at things this way, or even just in the kind of, standard form, so to speak, um, if this really, resonates with you and you're like, oh yeah, I've done a lot of work with that and I know exactly what this looks like, you know, other people might have a different perspective, but I think most of us are a lot more used to looking at dependent variable by itself, and then independent variable is the thing getting squared or cubed or square rooted or whatever it may be. Yeah. Okay, so let's jump into 6.2 then. Finding volumes using the disk or wafer method. Um, Disk or wafer, sometimes also called washer method, and we'll see why uh, hopefully soon. So let's look at a definition. Let S be a solid that lies between x equals a and x equals b if the cross-sectional area in plane px through x and perpendicular to the x-axis is denoted a of x, where A is continuous, then we define the volume of S to be, well, it's the limit of these, uh, the sum here, which turns into an integral. Let's uh, let's draw this out as a picture. I think that's quite helpful. So we have some solid, so a three-dimensional object. I'm going to draw X pointing this direction, although that's not the usual convention. And I'm just going to draw kind of a ball, like a sphere with its interior, just because that's easy for me to draw and visualize. But this could be any three-dimensional solid. Okay. Okay, so there's my solid S. Now, if I have a plane PX that's perpendicular to the x-axis, it's going to look like this, and it's going to cut through my solid S. In this case, this cross-section of a sphere is just going to be a circle, the boundary of the solid being a sphere. And we denote this area, this interior area, A of X. Let me get rid of one of those lines so you can see it a little better. A of X. That's this two-dimensional area here. So we have a three-dimensional volume, take a cross-section of it, that gives us a two-dimensional area. And we're saying that the volume of the solid is the integral of this two-dimensional area A of X as we take cross-sections starting at A and working our way over to B. Why, like, should that be the case? Why is that a reasonable definition? Well, we can imagine doing something like a Riemann sum here. Instead of having an infinitesimally thin cross-section, we could have a cross-section that kind of gives rise to like a little cylinder, right? We could imagine, let me get myself a little more room here. We could imagine that coming out of this cross-section, we have just a little cylinder like this. And that might be like an approximation to a little chunk, a little slice of our solid. If we go over to the right a little bit and take another cross section, we'll get another kind of cylindrical piece. It'll have a slightly smaller radius. If we go a little more to the right, we have another cylinder with yet a smaller radius. If we go to the left, we have another cylinder with a bigger radius and so on. And you can see that what we have here is a bunch of basically wafers or like little kind of filled in washers or discs that we're kind of stacking from the right going to the left. And then, of course, we uh, get to the biggest one. And then start getting smaller again on the other side. It's not the prettiest drawing ever because I'm getting lazy the more of these that I draw. Um, but going back down in radius, going off to the left. And you can see the kind of stacking these wafers next to one another and varying the radius, or perhaps for a more general solid, varying the shape even. But in this case, simple enough solid, we're just varying the radius, larger, and smaller, stacking these wafers together. If I have 10 or 15 wafers, that'll give me maybe a good approximation to this ball. If I had 100 wafers, it would be a much nicer approximation, much closer. If I had 1,000 wafers, even closer, right? The error from the ball actually cutting down like this, I'm overestimating a little bit here, underestimating a little bit there, but that error is going to get smaller and smaller the more wafers that I use. what is the size of each of these wafers? Well, it's the cross-sectional area times some little delta x, some little deviation in the x-axis. To make a volume, I take each of these little pieces of volume, the volume of each of these wafers, cross-sectional area times delta x. I add them up. That gives me an approximate volume. And then I limit as the number of wafers goes to infinity. And of course, implicitly, as delta x goes to 0. This is essentially the same as a Riemann sum. We're just using wafers instead of boxes. Let me destroy the evidence of my uh, of the fact that I failed art class. So that is, oops. So that is the basic idea. So let's try to compute the volume of a sphere with radius r. So we've already done some of the work up here. So we'll just kind of, copy this work down. I have my sphere with radius r. So if I look at in this cross-sectional area, this plane px, I have a circular cross-section. It's going to have some radius. And what's the radius going to be? Well, I know that my sphere of radius r, if I'm just looking at a vertical cross-section parallel to the x-axis, basically perpendicular to, maybe we'll call this the z-axis, I see that this radius is going to be the vertical height right here, right? That's going to be the radius over here. And in fact, I could even draw this radius straight up and down. Oops, I don't want to get rid of that whole thing. Can I just pick that black curve? All right, it's not letting me just pick the black curve, but I could draw this radius straight up and down even if I wanted to make it even clearer. So it's important to note that this radius, this height is not the radius r. This radius is r. And that height, that radius right in the middle, x equals 0, that's a special case where the radius is actually little r. But this is going to be different. This is going to be, well, if I give this the name y, x squared plus y squared equals r squared, solving for y in terms of x, y is going to be, we'll take the positive square root because we're dealing with the top here, square root of r squared minus x squared. So if I call this radius y, which is a function of x, if I pick a different x for my plane to be perpendicular to, if I move to the right or to the left, that's going to give me a different height. It's going to give me a different y value and therefore a different radius for my circular cross section. And the area of this circle is going to be pi times the square of the radius, or pi y squared. But y is root r squared minus x squared. So I've had to do quite a bit of work going back and forth between the geometric side of things and the algebraic side of things. As a side note, that's a very powerful thing to be able to do in math, to be able to, if you get stymied on the geometric side of things, can you jump over to the algebraic side and help you over that hump, or vice versa? But using both of those, we ended up with a formula for the cross-sectional area. And we see that we are integrating this cross-sectional area to get the volume of the solid. We're integrating over the x coordinates where that solid lives, from x equals a to x equals b, or in this case, from x equals negative r to x equals positive r, where a sphere of radius r, when the other two coordinates are 0, x is going to be at negative r or at positive r. So my volume is the integral from minus r to r, right, of my cross-sectional area, pi times r squared minus x squared dx. I can do a couple of things here to make my life a little bit easier. First, I realize that this is an even function. Using symmetry is another almost cheat code in math. Like if there is a symmetry in the problem, quite often if you respect that symmetry, you'll be rewarded. I notice that this is an even function integrated over a symmetric interval. I can double the value and just integrate from 0 to r. I can also pop that factor of pi out in front. The integral is a linear operator. Constants can come out, and it can split sums apart. So I have 2 pi integral 0 to r. The 2 came from the symmetry. I'm integrating from 0 to r instead of minus r to r, and the pi came out. That just saves me a little bit of headache with resolving negative signs and so on later. The fewer negatives that I have floating around, I already have, antiderivative at b minus antiderivative at a. So I already have an implicit minus floating around. And if I get even more negatives floating around, uh, I'm bound to make a mistake with a sign error somewhere. But integrating now, I get 2 pi times r squared x minus 1/3 x cubed from 0 to r. This gives me 2 pi times r cubed minus 1/3 r cubed, and then minus, of course, this evaluated at 0 is just 0. This does look nice as far as units are concerned. Units are always another nice check. If I had my radius measured in, say, inches, that would be a fair measurement for radius, or centimeters if you know, like, you know, whatever reasonable units. Then my volume, which I'm saying that's what this is, my volume should be in cubic units of length, and indeed it is. So that kind of makes me happy. That suggests that I might be on the right track. And if I have one of these minus 1/3 of them, I have 2/3 times 2 is 4/3 pi r cubed, r, good old familiar volume of a ball formula. Kind of as a side note, a sphere is the boundary of a ball. So the ball is the solid, the three-dimensional solid, and the sphere is like the surface of that solid. It's kind of like the two-dimensional membrane that covers the ball. So I'm trying to be a little bit careful about using the right terms here, but so this really should say a ball with radius r. But if you say a ball, then you know most people before I say that, most people um, think of it being more generic. Sphere seems a little more technical, but actually in math, the technical description for this is a ball. So any questions so far? So a little note, if our solid can be obtained by rotating a function y equals f of x about the x-axis, then our cross-sectional area is going to be pi y squared, and our volume is going to be inner a to b of pi y squared dx. So in the special case of a solid of rotation or a solid of revolution, where we can imagine constructing this sphere by taking this function up here, rotating it about the x-axis, right? That's going to make a mirror copy down here. And as we rotate it about in 3 dimensions, it's going to trace the outline of a solid or trace the boundary of a solid. And that enclosed solid will be a solid of rotation or a solid of revolution. In essence, it has a rotational symmetry when rotated about the x-axis is the point that we're making here. If you rotate the solid about the x-axis any amount, it looks exactly the same. If that is true, then we have a little bit of a shortcut. So let's take a look at this example, and we'll do this one kind of from first principles. We did the last one a little bit, you know, in a couple of different chunks. We'll do this one start to finish, just working on this example. Compute the volume of the solid obtained by rotating the region R about the x-axis, where R is the region bounded in the first quadrant, bounded by y squared equals 8x and x equals 2. So y squared equals 8x, or y equals square root of 8 times square root of x. So it's going to look basically like y equals square root of x. Maybe I'll draw this in blue. And just to be clear, this is x, this is y. And then in green, I'll draw x equals 2. This is our region, and we're rotating it about the x-axis to create our solid. So we're rotating it that way. Let me get this out of the way here. So what's our solid going to look like? We have this upper part here. When we rotate it around, we get a mirror image for this lower part. And we see our x equals 2 up top here. Comes down as well. And that traces out like this kind of top surface. So we have something that looks kind of like a bowl, like a filled in bowl that's on its side. And if I imagine taking a cross section with a plane perpendicular to x, I'm kind of taking my time here to try to draw these pictures pretty nicely so that it's easy to tell what's going on. I think spending, 50% extra time drawing a nice picture is well worth the time investment. And if we jump over here and look at plane PX perpendicular to the x-axis straight on, we see we have a circular cross section again because we started with that function in the xy plane and rotated it around. So it's naturally going to be a circular cross section when we have a plane perpendicular to the x-axis. And it's going to have radius of y, right? The radius is going to be this height there, which is just y, the y associated with this value of x. My area is a function of x as pi y squared, and that's exactly what we set up here. We can see that from first principles, or we could have taken a little bit of a shortcut using that note. I see that x is going from 0 up to 2. So my volume is going to be the integral from x equals 0 to 2 of pi y squared dx. And what is y squared? Well, y squared is just 8x. or this is going to be 8 pi. The integral of x is 1/2 x squared from 0 to 2, evaluated from 0 to 2. Or this is 4 pi times 4 minus 0. 16 pi is our answer. So any questions on that one? Okay, let's see how far we get through this one. We might not get all the way through, but if we don't, then maybe I'll leave this as an exercise for you to finish up, and we'll uh, just briefly talk about it, just give the answer next time maybe. Okay, so another example, compute the volume of the solid obtained by rotating r about the y-axis here. So be a little careful. We're not rotating about the x-axis in this example, but about the y-axis. R is the region bounded by x equals 0, y equals 3, and x equals 2 root 10y. Or this would be y equals, so if we square everything, we get x squared equals 4 times 10y. Oops. So this is x squared equals 40y, or y equals 1/40th x squared. So we see this parabola opening up. The line x equals 0 is the y-axis. We have y equals 1/40th x squared, or something like this. We have y equals 3. And we have our region. And then remember, we're rotating this about the y-axis. Note that if we rotated about the x-axis, we would get a different volume, and we get a different solid and a different volume. So what does this look like as a solid? I have this piece over here, mirrors to this piece over here when I rotate about y. This green bit at height y equals 3 comes over to the other side as well. And again, I get kind of a bowl shape, but in this case, it's a bowl that, a solid bowl, a filled-in bowl that's kind of upright. That's kind of the right direction. Now, I suppose that I could take cross sections perpendicular to x and force the issue, but my cross sections are going to look really wonky, right? I'm going to get something like this. I don't really want to find those cross-sectional areas. I really want to make use of the symmetry in this problem. And the symmetry is about the y-axis. I'm going to choose to take my cross sections, I'll call them py, that are perpendicular to the y-axis. These cross sections are going to have radius x, right? Everything is similar, just kind of mirrored from the last problem. And my area of y is going to be pi x squared. And from here, it's pretty straightforward to do the rest, right? The volume is going to be integral 0 to 3, integral y equals 0 to 3 of pi times 40y dy. And you can finish this one out. That's not a difficult integral to do. Any quick questions before we break for today? Stop the recording.